This is a video I've made to present you some ideas I had about how we could implement this system to control Baxter for the Amazon Picking Challenge. This is the architecture of the system we are considering, and I decided to prepare this video because I was trying to go ahead and build the localization mapping object pose recognition models, and I had some difficulties on how those models will communicate with the high-level decision making and monitoring model. So in doing that, I built this state machine. This is the state machine I'm proposing for the high-level decision making in monitoring monitoring model. In this state machine, the different items have the following meaning. So in bold, we have the name of the state, or which one of the state of state machine. In italics, we have the conditions or flags for the state transition. These state transition flags are examined each cycle, and the state machine will run at, say, about 40 Hz or more or less this frequency. In color, in the state machine have the information or variables that the state machine publishes, or the high-level decision-making monitoring model publishes, together with the state to all other models that are interested in this topic in the architecture. So these variables may be binary or non-binary. Binary variables are only shown when they are true in the state machine, and non-binary variables are only shown when they have a valid value or a value that will be considered by any one of the other models. So let's go back to the state machine then. So it starts in this state that's called wait for work order. So the work order is the work order from Amazon and tells which items wants Baxter to go and pick up in the shelves, or the bins in the shelves. So this state continues to be the same state as long as the order has not arrived. So this symbol, this tilde symbol, says that this binary variable, order arrived, is not true. So when this variable is true, it means the order has arrived. For example, a file containing the order appears in a specific directory. The state machine leaves this state, it goes to this state, select item. In the select item state, the state machine publishes the state itself. It always publishes its state, but also two variables that I will talk about to you later. So these variables are transmitted by the high-level decision-making monitoring model to all the models and are listened to by the interested models. So the state machine stays in this select item state until the robot has moved to the origin. Origin is a specific position of the robot where it can start moving to any desired bin. So when the state machine got one item and is at the origin, the arm is in the origin, the arm of Baxter is at the origin, it can move to this next state. And when in this state, if there is no more items to be picked up, so the robot has performed all the pickups that were in the order, the system goes back to wait for a new order. But if there is one item in the list and the robot is at the origin, it moves to this state, move to bin. So at this point, the state machine knows the bin ID, where the object of interest or the item of interest is. So when the state machine is in this state, it issues the other information that will tell the robot to move to the front of the desired bin or bin ID. While it doesn't happen, the state machine stays at the same state. But when this flag is true, at the bin is true, so the state machine moves to this next state, which is map and detect object state. In this state, the state machine will publish those informations and will wait until the bin is mapped and the object has been detected. When both things occur, it moves to the next state. While no one or both of these conditions are not true, the state machine keeps in the same state. So when the bin is properly mapped and the object has been detected, the state machine moves to this next stage, which is move closer to the object. At this point, the high-level decision-making monitoring module already knows where the object is, and then it can move close to the object. So this information will tell the state machine to move closer to the object in addition to other things that I will talk about later. So, and the state machine will keep or stay in this state until the arm is close to the object. So while it's not close to the object, it stays in this state. When it's close to the object, or in the position that is proper to grip the object, to grasp the object, the state machine moves to this state, this is the grasp state. And we will issue the proper commands to the remaining models that will allow the robot to grasp the item. When the object is grasped, it moves to this state. While it's not grasped, it stays in this state. And once the object is grasped, the state machine get to this state, which is move arm away from the bin. So in this state, the arm will gonna move away, slightly away, or take the object out of the bin and in free space. And when it happens, when the arm is clear from the bin, it then goes to the next state that put in order bin, or put the item in the order bin. So the arm is gonna move and take the object close to the order bin, and then leave the object so that it falls in the order bin. While this did not happen, the state machine stays in this state. But when the item is left in the order bin, the state machine then can move back to select the item state, and the next item of the work order will be selected as soon as the arm is in the origin, and the state machine receives this information that the arm is in the air, is at the origin. It has the item that it needs to pick up. It's go back and do all over again. As soon as it gets to this state and there is no more items in the list, it goes back to this initial state where it waited for another order. So let's check how the remaining information is manipulated by the other models of the system. So the high-level decision-making and monitoring module has the purpose of monitoring errors in the process and do high-level decision-making. Currently, my proposal is to make those high-level decision-making that I have just shown you in the form of that state machine. In the simple version of this model, it will implement this state machine. In a more refined version, it will deal with the complete challenge of, for example, select all objects in the list that are not in the sequence in the list itself, but select to pick the easiest item, for example. Better monitoring of action. You may have noted that there is no error correction that I could add here. For example, in this state, if the localization is lost, for example, the system does not know, for example, for some reason where the arm is, it could go back to this state where it would move again in front of the beam and repeat the mapping and so on. So I didn't add these modifications at the moment, but in the final version we would need to have those other behaviors properly configured in the state machine, or in some other implementations of this model that does not use a state machine. My proposal is that we keep improving the state machine if we agree on using it in the first place. So as I said, this model would operate in would be a loop, and at about, say, 40 hertz, where every time we would check the state and the conditions and move from one state to the other according to the flags the state machine will receive from the other models. So let's go and have a look in the other models. So the first model was the one that I was thinking about when I was decided to do the state machine, which is the localization model. The purpose of this model is to provide an accurate estimation of the pose of the sensor in the arm with respect to the map. So it's not exactly the purpose that Costas has proposed. We still didn't fully agree with how this would work, but that's my proposal. I hope when I explain the other part of the system, you see why I'm proposing this type of localization. So the purpose of this model is to tell where the sensor in the arm is with respect to the map. So the sensors in the arm is fixed to the last part of the arm and moves together with it. In the simple version, this localization model will only publish the pose of the sensor in the arm with respect to the robot, not with respect to the map, and it will use the arm encoders to do that. So assume that the robot in a specific position, and using the angles of each part of the arm, which compute where the sensor is in the world with respect to the origin of the robots. But in the final version, the model will publish the pose of the sensor in the arm with respect to the map. So this localization model operates in two modes. One that I called LSTD mode, or localization standard mode, and the other that I called not in the localization standard mode. These two states of this module, the localization model, are governed by a binary variable that is published together with the system state. So the state machine will publish this variable, and when it's not true, the localization model will publish the pose of the sensor in the arm with respect to the robot using the arm encoders. The word reference frame is always provided by the map. I'm going to talk about the mapper in a minute. The other mode of operation is the localization standard mode. In this mode, the localization model will publish the pose of the sensor in the arm with respect to the map. And for that, the model will use the Kinect point cloud and the map the current map to compute the pose of the sensor with respect to the map. So using this information, other models that will take care of the movement of the robot would be able to localize the full robot in the map. But this localization model will only publish the pose of the sensor in the arm with respect to the map. And in this mode, the standard mode of operation, it will not use the ARM encoders for doing that, but only the map and the technology that is inside it to use the point cloud and image to localize the camera in the Kinect, or the sensor that we use connected to the arm. And to go before going back to the state machine, I would like to discuss the mapping model. The purpose of this mapping model I'm proposing is to provide the map of the world for collision checking purpose. And in a simple version, it will only publish the model of the shelf. So we're going to publish the model of the shelf in the world using ROS message. And in the final version, it will publish a map of the target bin, of the real shelf, and the surroundings of this target bin. So the mapping has also three modes of operation, which are mapper simple mode, mapper standard mode, and mapper freeze mode. In the mapper standard mode, it will publish a fixed model of the shelf in world coordinates at an approximate expected position with respect to the robot. So in this mode of operation, it will only publish for example, a snapshot taken from the shelf and in the past. No, it's not one online snapshot of the shelf. In standard mode, this model will build and publish a map of a target bin of the shelf and its surroundings continuously. And this will take some time to build the first map. So when the map is finished, this model will publish the flag mapped. That is, when the map is ready, it's going to publish this flag mapped that is used by the state machine. And the final mode of operation is the freeze mode. So the mapper, when it's in freeze mode, it will publish the last map of the target bin, of the real shelf, and the surroundings continuously. Always publish as frequent as possible, say 20 times per second we publish this map. Going back to the state machine, I'm going to try to explain you the rationale behind these two models and how they operate. So, say that we are in this state and we are moving to the front of the bin. So when we are moving to the front of the bin, the mapper system is going to be in the simple mode. So the simple mode will allow some level of collision detection by the other models, but it will not be precise. So this model should be used with care, or the mapper should publish, say, the shelf a little bit closer to that it will really be, in case of online, in case of not safe operation, say. So when you move to the bin, the mapper is going to publish the saved map, an old map that just represents a certain condition of the shelf that can be used for obstacle detection. So when the arm is close to the bin, or in front of the bin, so we in this moment are going to do the mapping. So the state machine will tell the mapper mode to go to the standard mode of operation. So in this mode of operation, the map will be actually built, and a fresh map of the shelf in front of the arm. And at this point in time, we already know the object ID and other things will happen, but using this mode of operation, we can then guarantee that we are going to have the map. When the map is done, I can then move to the other state depending on the detection or not of the objects of interest. So let's go ahead and see how this model will operate, the object pose recognition model. So the purpose of this model is to identify the pose of an object or item in the shelf. In the simple version, it will do this task for a single item in a limited number of positions. So we can put the object in the shelf in a precise, more or less precise position. In the system, this model will be able to find the position of the object. But in the final version, we have to solve the problem of detecting the object for all items and deal with the situation where we have more than one item in the same bin of the shelf. So this model will publish the object pose and operate in two modes. So is the object pose recognition standard mode and not in standard mode. When this model is not in standard mode, it will do nothing. When it is in standard mode, we try and publish the pose of the detected object with respect to the map. In addition to publish the pose of the object, it also will publish the detected flag. When the object is found, this system will publish this information saying that the object has been detected. So let's go back to the state machine and have a look again. And here we see we have the object ID, which is used by the object pose detection model. And using this object ID, you're going to search the image captured by the sensors in the arm to detect the object, and if the object is detected and when the map has been finished, the mapping has been finished, so the system can move to this other stage. So let's go ahead and have a look again in the mapping module. So this model has three states: simple mode, standard mode, and freeze mode. So let's go back to the state machine, and when we are in this stage, in other states, we are going to have the map in the simple mode, where it publishes a static version of the shelf. But when it is in this mode, it goes to the standard mode and build a fresh map of the shelf. And even when it's all the time it is here in this state, is building this map. But as soon as I move to this state, the map goes to the freeze state mode, where the version of the shelf that was just being mapped is freeze, and the map continue to publish the same version of the shelf. Why we are using this mode? Because in this point of the process of taking one of the items off the shelf, the arm is going to move closer to the objects, and the sensor we have will not be able to continually mapping, because the object will be too close. So while in this state, I freeze the map. And again, in this state where I'm grasping the object, because I'm very close to the object in this moment, I also keep the mapper in the freeze mode. And once again, when after grasping the object, when I move the arm away from the bin, I'm still using this map because it's the fresher version of the bin. After leaving the state, when in a point where the arm is away from the bin, I go back to the mapper standard mode, where it publishes one complete version of the shelf, a safe version of the shelf, so that the robot would not collide with the shelf when doing these movements. And finally, when it go back to this stage where I'm gonna pick up another item, I'm still in this simple mode, where it publishes one old version or one complete version of the shelf that will allow the system to avoid collisions with it. So let's go ahead and have a look on the motion planning model. So in the motion planning model, the purpose of the motion planning model is to compute and publish trajectories for the robots. So it's a bit different that we had before. So trajectories, by trajectory I mean a sequence of poses and times. So I suppose that in the initial of one of the entries of the trajectory, I have a pose, and the new pose and the time I will stay in this part of the trajectory, and at the end of this element of the trajectory I get a next one where I assume I was in the previous position and now I want to go to a new position during a specific period of time, and so on. So the purpose of this model is to compute a trajectory with a sequence of arm states and times. In the simple version, we are gonna publish predefined trajectories or compute and publish trajectories from the current position to given target position, not considering obstacles. In the final version, I'm going to do the same, but avoiding obstacles. So this motion planning model operates in two modes. The first mode is publish predefined trajectory, say predefined trajectory X, where X can be several different trajectories, and I call this mode MP2X or motion planning 2X. And in the other mode, it computes and publishes a trajectory from the current position where the robot is to a target position X dash, and I call it NP2X dash. So in this mode of operation, this model will publish a predefined trajectory. This predefined trajectory X will depend on where the state machine is in this sequence of states, and this model will publish simply publish this trajectory. We expect in this case that the robot will follow the trajectory, and the origin of the robot when performing these commands, or when the motion plan is publishing this trajectory, the origin robot in this case is fixed in the world or in the map, which is the origin of the board. And when the motion planning verifies using the arm state that the robot is at their origin, after executing this command, this MP2O or motion planning to origin, this flag will be true. And when the motion planner sends the command motion planner to beam, when the arm is at the beam, this model will publish at the beam, and when executing the command motion planner to order beam, this flag item in the order beam will be published by this model. So this is one of the modes of operation. The other mode of operation is motion planning to X dash, where this X is different from the other one, because in this case, this model will continually compute and publish and monitor the trajectory to move the position of the sensor in the arm. Look, move the position of the sensor in the arm with respect to the map to the target position X dash. So always with respect to the map. So in this case, I'm interacting with the real world, and to avoid problems with uncertainties related to the position of the robot, that I'm proposing this form of operation. So in this form of operation, at the beginning of each step of the trajectory or the movement, or a series of steps or series of entries in the trajectory, the system will compute the position of the robot origin, or find where the origin of the robot is with respect to the pose of the sensor in the arm. So it will reset the where the robot is with respect to the map, because it might not be precisely in the position that we would expect because of errors. And once verifying that, this model will repeat this procedure, which will be to plan from the next step, from the position that the robot is, to the next step where it would like to send the robot to, always updating where the origin of the robot is and consider it valid the position of the sensor in the arm and the map. So the robot would, this model will repeat it until the sensor is in the X dash position. So there are situations where I need this mode of operation, and in the two situations that I need, the system, when it executes motion planning to OB dash, the robot will publish this model will publish this flag called close to the object when it's finished getting close to the object, and the flag clear from beam after execute move to AB dash, or move away from the beam. So let's go back to the state machine to see how these variables are used. So let's say that we are in this state and the order has arrived. So I get to the select item stage. This state, the motion planning model will receive this command, move to origin. So it will send a trajectory to the arm that will follow without feedback movement from the point where the arm is to the origin. And after I get this N item, I move to this state, move to the beam where this motion planner will receive the command move to the beam. So in this state, the arm will leave the origin and move in front to the beam. At this time, the system will also this model, high-level decision-making monitor, will publish the beam ID so that the motion planning will know to what beam it should move. And the mapper will be in the simple mode, publishing the a fixed version of the shelf that can be used if necessary to allow collision-free movement from the origin to in front of the selected beam, the beam that is specified in the order. So when the arm is at the beam, so when the motion planning sees that the arm is at the beam, it will publish this flag and the state machine will move to this state. In this state, the motion planner will receive the motion planner will know that we are in this state, and although I'm not sure if it should send any movement commands to the arm. Perhaps it should. The system then will be able to map that beam. Once the beam has been mapped and the object has been detected, the state machine can go to this state where the purpose is to move the arm or the end effector of the arm close to the object. So in this stage, the motion planning will be at the stage motion planning to OB dash, or motion planning to close to the object. So in this state, it has to consider the fresh information about where the actual beam is, where the shelf is, and in order to avoid collision. So and also it's important in this state to know where the object is, and so be able to move the arm to precisely in front of the object, or a position that is appropriate for grasping. During the grasp state, the map will, in this state, the map will be freezed, and the motion planner will hand out the control of the robot to the grasp model. Let's have a look in this modeling. So what the purpose of the grasp planning model is to identify the grasping configuration of the object and a strategy of the robot hands to grasp it. So in this simple version, this model will assume only grasping of using the gripper, and that objects are in standard poses that will be easily dealt with by this grasp planning model, and free of obstacles in front of the gripper. In this simple version, this model will ignore the map. So my idea for this this grasping model, the simple version, is that when, let's go back to state machine, when I move to close to object and get to the state, the object will be exactly in front of the hand. So the grasping movement will just be moved a little bit in the direction of the object, and then grasp or close the gripper so that it would get the object. So that would be the simplest grasping possible that we can use to test the other models and improve this state machine. So going back to the grasping model, so in this simple version it's going to do that. In the final version we'll do more or less the same, but taking the map into account, and it will also have to deal with multiple different objects in different configurations in front of the arm. So this grasping model has two states or two modes of operation: grasp and not grasp. So when it's not in grasp, it is doing nothing. When in its grasp condition, it will continuously compute, publish, and monitor the sequence of movements that will grasp the object. When the object is grasped, or when this routine, this trajectory of sequencing of movements of the arm are complete, this model will publish the grasped flag that is used. Let's go back to the state machine. That's used by the state machine to leave the grasp stage to the move away from the being stage. So in the move away from the being stage, the mapper model will publish a freeze version of the map. The localization model will be in the standard mode, so I will have proper localization with respect to the shelf if the robot has not moved it. And I will use in this situation the motion planning to away from the beam. So in this condition, the motion planner should use the map and the pose and move the arm away from the beam. When the arm is successfully outside the beam, so I can go back to this stage where I'm going to move the arm to a position where I can leave the object in the beam. So I'm send this command to the arm. So the motion planner will send this command to the arm: move to the other beam, and then leave the object so that it could fall in the other beam. So finally, the module control has the purpose of providing controls so that the robot would move, receiving the trajectory sent by the grasp planning or motion planning models. So in the simple version, it will just follow the trajectory computed by the motion planning or the grasp planning models. So those planning models will send trajectories, which are sequence of pairs where I have a position of the joints of the robot and a time, that is, I want the robot take to move from the current position to the position that is specified. So it's a very simple model. But in the final version, this model will provide perhaps a low level of feedback so that the planning models will know how good is the current trajectory. So that's it. I hope you like this proposal, and I'd like any feedback that you have so we can improve it. So my idea now is just going back here to the three models that I'm working with, is to build this localization model that receive and publish ROS messages according to this design, and this model again that receives and publish ROS messages according to this design, and the object pose recognition model that also receive and publish ROS messages according to this design. And if you agree, I would like also to work on the implementation of the high-level decision making in monitoring model, so that I would implement this first version of the state machine. Because I've done that before. I've done some implementation of state machines that, of course, it's not something really difficult to do, but I'm offering myself to help on that. Thank you.